Okay, we've spent a few classes on graphing exponential functions. Now we have to kind of shift gears into looking at graphs of logarithmic functions. Okay, so that's the difference here that you need to recognize. Maybe if we look back at the beginning, kind of the organization of this here. These two are tied together in that we're looking at graphs of exponential and logarithmic functions. We first looked at exponential functions, just the basic graphs, like what does 2 to the x look like, what does 3 to the x look like, and so on, right? And then we started doing some transformations, like if you put a plus 1 there, how does that change the graph? If you put a plus 1 here, how does that change the graph? If you put a times 5 in the front, how does that change the graph? Now, you may not be completely to the point of understanding everything with that, but hopefully with having a period last time to work on it and not moving ahead, you got some of that. Okay, so we're kind of moving on to this, even though you might not be completely comfortable with this, right? The quiz that we're going to do later today that we've been putting off is on that, right? I want to allow you some time to learn it before we start doing any assessment on it. So, going back to this. At first, we need to know what the basic graph of a logarithm function looks like, and then you can start doing some transformations to it, just like you did for exponential functions. We already actually know that logarithms and exponents are related as inverses. Like on your calculator, that button is the inverse of that button. Log x and 10 to the x. Those are inverses of each other, right? You don't have these buttons, but 2 to the x would be the inverse of what button if you did have it? Log base 2 of x, right? And in theory, in grade 11, you know what the inverse of a function is? Well before grade 11, you learn what the inverse of a function is. You probably learn it in grade 2 or something like that, right? If somebody says 5 plus 2, the operation of adding 2, what's the inverse of adding 2? Right? So I'm not trying to insult your intelligence here, but it's not a concept that's all that difficult. The inverse of something is the operation that undoes it. So if you add 2 to, I'm trying to insult my own intelligence here. I'm thinking of subtracting. 7, let's get it right. If I want to go back now, I am insulting your intelligence. If I want to go back now, obviously the opposite inverse operation. Let's quickly make it a little more complicated. This is embarrassing. If I had a function like this, y equals, take some number, cube the thing, and then add 2. Think about the operations involved there. So you take an x value, you cube it, and then you get something, and then you add 2, right? And then you get your y value. If I want to go back now the other direction, what operations do I have to do, and in what order do I have to do them? You have to do the opposite, the inverse operations. If the first thing I did here was cubing the thing, and then I added 2, when I go backwards, what order do I have to undo them in? What do you have to do first? You have to subtract 2, and then you have to do the inverse of cubing, which is cube rooting, right? Like the inverse of cubing is cube root, right? Or raising it to the power of 1/3. You've probably learned in grade 11 that you could do this by switching the x and the y, and then solving for y. Does that sound in any way familiar? Switching x and y, making it x equals y cubed plus 2, and then solving, right? Because when you move this over, it becomes minus 2. And then when you get rid of that cube, you get, right? When you do the cube root of both sides, you get y as cube root of this. You could also express this with powers. If you don't have a cube root button, but you do have a power button, how could you write that with powers? The cube root of x minus 2 is the same as x minus 2 to the 1/3, right? You could do it to the power of 1/3. Same thing. Anyways, you maybe could just write that inverse by just looking at it and saying, well, if I cube it and then add 2, To undo it, I have to minus 2 and then cube root it, right? If you think like that, right? Like this one that's down here, if you have that function, if it says times 2 and then plus 4, the inverse function is going to be what? What's the inverse function going to be? X minus 4 and then divide by 2, right? That's what it is. If you graph both of those, you'll find out how they're related. Did you look in grade 11 at how the graphs are related for inverse functions, or did you focus on the algebra part? Because let's look at the graph of these two inverses here, this one and this one. But I'm going to look at it on there. Okay, so that's this one, x cubed minus 2. Okay, except was it plus 2 on the other page? I probably made it opposite, didn't I? Oh well, you get the idea here, right? Let's go back here. My graph is minus 2 here. If that's minus 2, obviously then the inverse is going to be plus 2. Okay, so we'll stick with that so it matches my graph. Easier to change that. The inverse of that is going to be then x plus 2, cube root of x plus 2. So that's what this one is, so we'll put that one on there. And maybe you looked at those graphs last year, how those are related to each other. If you're doing the opposite operation, think about where this point is going to go. Where is that point going to go? The point that's -1, -3, where is that point going to be? Where's the corresponding point on this inverse function? Where's the one that corresponds to that? Remember, if you're undoing the operations, like the original function took a -1 and turned it into a -3, right? The original thing would say, take -1 and turn it into -3. If I'm going back, what's going to happen? Take a -3 and turn it into -1. If -1, -3 is on the original function, what point has to be on the inverse? -3, -1. You reverse the coordinates, right? The coordinates of all the points on the inverse, all the points on this inverse are going to be just the reversed coordinates of this. So there's, maybe not, there is. Oh, I got it because I did this. Okay, there's that. There's that point that corresponds to this. If you trace this out now, okay, as you move along here, all these points are the same points, but the coordinates reversed. Anywhere we stop here, like 0, -2 is -2, 0. Anywhere you stop here, that point right there, doesn't maybe let me stop right on there, but -1, or 1, -1 is the same as -1, 1, right? 1, -1, -1, 1. This point up here, that one becomes the same because they intersect. Any point is related by those coordinates are reversed. Okay? It's a reflection in that line. When you draw the inverse, that line y equals x. Okay, the inverse is a reflection in that line. If you want to draw the inverse of something, you can take a point and then just reflect it across that line, right? This point is directly reflected over to there. This point is directly reflected over to there, right? This point would be right there. Some of that you may have talked about in grade 11. Maybe some notes over at the side right here, just about how those three ways of relating a function and its inverse. A function f of x and its inverse, f with the little -1 of x, which you don't say f of with the little -1, you say f inverse of x. It's a bad choice of notation because you get confused then with exponents, but a function and its inverse are related as follows. Okay. When you're talking about the graphs are reflections in that line. Reflections. Boy, a little trouble on a Monday morning here. Reflections in the line y equals x. Okay, that's the graphs. The graphs are reflections in the line y equals x. How are the equations related? What did we say? The equations are related as they're the inverse operations. If you switch x and y, that creates the inverse, right? Switch x and y. And solve for y. Okay, i.e. you end up with all the inverse operations, right? Inverse ops in reverse order. Okay, inverse operations in the reverse order. And then the last thing, let's say points or a table, right? If you're looking at numbers, points or a table, how are they related? Coordinates are reversed. All of these are the same thing, right? Reflecting in the line y equals x is the same as switching x and y in the equation or reversing the coordinates in points or in tables. Okay? So we have those three things. So some of that you already know, some of that you do not know.